Hey everyone, my name is Alvin Dikefo. Here's my final presentation for Data 670. And for my project, I'll be analyzing the impact of COVID-19 on the public transit systems of New York City, Washington, D.C., and San Francisco. So here's an overview of how my presentation will go. We'll talk about the project scope, KPIs, data set, description, visualizations, predictive models, result, conclusion, future analysis, and then I will leave room for questions. So here's the first part of my presentation, the project scope. Basically, according to data, approximately 11% of Americans use public transportation on a weekly and daily basis. With that said, the data analytics problem that I am analyzing is understanding how an increase or decrease in COVID-19 cases and deaths could have either positively or negatively impacted these transit ridership numbers. So for the key performance indicators, I have three. So the first key performance indicator is basically making sure that each data set has a relationship, because based on that, I'll be able to now identify a target variable. So that's the first KPI. And then the second KPI is basically identifying what factors lead to an increase or decrease in ridership counts. And then the third KPI is basically answering what city or transit agency had the most fluctuation in its ridership count due to COVID-19. So, so for this project, I'll be using three different data sets. So the first data set, which is a primary data set, that will be the daily transit ridership data set. And then the secondary data set will be the United States COVID-19 cases data set. So that's a data set that will basically hold most of the COVID-19 information. And then the third data set is basically the death by states and COVID tracking project data set. Basically, what that data set does is it's more of like a juxtaposition to my secondary data set, just to make sure that the COVID-19 data matches one another. And then in terms of my data set preparation, so the first thing I did before I even began transforming the data was to first create a database in SQL Server 2019 to host the data. So, and then after the database was created, each of the three data sets were loaded into individual tables in SQL Server 2019. And then just a quick overview. So before my transformation query, you see right here, the file size was about 100,000 records. That was before my transformation query. And then after my transformation query, the file size, like the final data set, was about 10,000 records. And then, like I mentioned earlier, so the relationships on each data set were built on the date and states column. So those were the columns that I used to basically build a relationship with each tables or each data set. And then on my handling of missing data. So basically the way I handle the missing data varied. So let's say in a string column, let's say if a variable had if a variable had like string data, say for example, like names and stuff, if there was a missing data on a string column, I'll basically replace that missing data with a no data value. And then on the numeric column, if there was if a numeric column had missing data, I'll either replace it with either 0 or sometimes the average of like the total average of that column. So that was how I dealt with my missing data. So now let's talk about the visualization. So overall, in my project, I had a total of 5 to 6 different visualization, and then each visualization basically had its own role. So the first visualization that I did was basically the total ridership per year, the total ridership count per year, which as you can see right here. So basically this visualization gives me like gives me like an overall ridership count for each of those three states combined together. So based on the results from my visualization, I found out that 2021 had the most ridership count. So New York City, Washington, D.C., and San Francisco combined had a total of 835 million ridership in the year 2020, and they had a total of 642 million transit ridership in the year 2020, and about 543 million in the year 2022. But there should be an asterisk on the 2022 data, because the 2022 data from a project only runs between the month of January and June, so it's basically incomplete data. But later on, I did some forecasting as well, and then I'm basically anticipating that the 2022 ridership count will definitely eclipse that of 2021. So, and then my second visualization basically just gives me a breakdown of the ridership count per city. So New York City basically had the most ridership count of for each of those 3 years. So my data set, so the years used in my data set starts from 2020 and ends mid 2022. So so within that time span, New York City had a total transit ridership of 1.1 billion, followed by DC of 200 million, and then followed by San Francisco with 56 million ridership counts. And then later on, I had another visualization that basically helped me understand what factors led to an increase in ridership count. Like, let's say, what would cause the ridership to go up during the COVID-19 pandemic, and then uh, based on the result, uh, so the ridership count in each of these three cities combined together would basically increase by 3.9 million when the total COVID-19 cases were 28 or less. So each time, so maybe this was at the beginning of when COVID-19 had just started spreading, but for some reason, the visualization found out that when the total COVID-19 cases were less than 28 for that day, the transit ridership would increase by 3.9 million. And then next one is and the next visualization basically predicts what would decrease the ridership count. And then based on the results, the ridership counts, or the transit ridership counts would decrease by almost 900,000 a day when total cases were above 28,000, and would also decrease an additional 876,000 when the total debt was between 1 and 8,000. So whenever there was a total COVID-19 death in that day, yeah, the transit ridership would go down in these three cities. And then my fourth visualization basically does like a forecast in each of the cities. So what I'm trying to do is I'm trying to forecast the ridership growth to the year 2024, and then based on my forecast analysis, the result shows that New York City 2024 ridership forecast is set to increase to up to 3.4 million ridership per day. So by the year 2024 in New York City, there will be an average increase of there will be an average ridership count of 3.4 million a day. And then DC, there will be by the year 2024, there will be an average ridership count of 310,000 per day, and then in San Francisco it was 110,000 per day. And then my final visualization basically does like an overall forecast on the total ridership count in these three cities for the year 2020, for the year 2024. And then based on the results, the overall total ridership count for the year 2024 would be about 950 million. And then the next technique I'll be analyzing or talking about are the predictive models. So my project basically in my project, I'm basically using three different predictive models. So the first one is a decision tree. So basically, I'm using the decision tree to identify what variables have the strongest predictive strength towards the relationship count. And, and in this scenario, the relationship count is my target variable. And then the second model is basically the k-means cluster. So basically what this model does is it groups the data in cluster to help find similar occurrences within the data set. And then my final predictive model is the neural networks. So the neural networks basically helps me recognize correlation and hidden patterns within the data set. And then here are the results from my predictive models. So in the decision tree, the outcome basically shows that total cases and confirmed cases variables basically have the strongest predictive strength towards predicting the ridership count, which was what my visualization as well found. So, and then based on the result, it shows that low COVID-19 total cases and confirmed death would increase transit ridership, and then high COVID-19 cases and confirmed deaths would decrease transit ridership. And then for the k-means clusters, it shows that cluster one basically is the most dominant cluster where COVID-19 concern cases, where the patients with COVID-19 where the patients agree that they have COVID-19. So that's the most dominant cluster. And then cluster 5 is basically the most dominant cluster where the patients or where there is no data to support the fact that this patient has COVID-19. And then cluster 4 is basically the most dominant cluster where the patient does not agree that they have COVID-19. So basically this helps me understand the similarities in the COVID-19 classifications and stuff like that. So that's what the k-means cluster helped me with in this scenario. And then the next predictive model are the neural network. So for these predictive models, I built it using 3 nodes, and then they each have their different weights. So node 1, that's the weight from node 1, and then node 2 has a much smaller weight from node 1, and then node 3, that's a weight over there. And then based on my Garson graph for the neural network, it shows that the confirmed death, confirmed cases are the variables that impact the COVID-19 concern cases the most. And then the model accuracy for this project was 98%. And then now it's time for the conclusion. So basically, from the analysis of my project, the conclusion I made was that an increase or decrease in COVID-19 daily cases and death did in fact have an impact on the transit ridership count. And then to answer the question for my second KPI, for my third KPI, New York City was a transit agency impacted the most by COVID-19. And then one other issue I faced with my project was the fact that I did not have sufficient data to do pre versus post COVID-19 transit ridership analysis, and that was because the data I got, like my the primary data set, which was a transit data set, only had data from between 2020 and 2022. So there was no data pre-2020. So, and any data pre-2020, that would have been the data that I could have used to, analyze a transit system ridership count before the pandemic. So that was one of the limitations I had for this project, was just limited data. And then the third one basically confirms my forecast and analysis that says the combined yearly ridership transit ridership count for each 3 cities would increase up to 915 million by 2024. And then lesson learned and future analysis. So basically, while working on this project, I realized that understanding the data at hand is key to a successful analysis. So there were scenarios where I had to, step back and, try to understand the data before moving forward. So that was something I realized, that understanding the data is key to a successful analysis. And then properly transforming and cleaning the data is very important too, because when you properly transform or clean the data, you're then able to now tell the story about that data with no problem. And then for the for the visualization and predictive models, I basically, one of the conclusions I made, it was that a good analyst should have the ability to produce both technical and non-technical analysis. So this is something I learned while doing the project, because it's good to be technical, but at the same time, you want non-technical users to be able to read and translate your work. So sometimes uh, telling the story of your data in layman terms help non-technical users as well. And then one other thing I realized after going through a lot of back and forth on my predictive models was that a good analyst should be able to know the pros and cons of each predictive models, because not every predictive models would work with your data set. Or so sometimes taking your time to understand the pros and cons of each predictive models might save you time down the road, So that's one thing I learned. And then finally, I also learned that every visualization should be able to tell a story. I mean, no one wants a boring visualization. So always have a visualization that a user can learn something new by looking at that visualization, or that visualization should be able to tell a story. And then in terms of the future analysis regarding my project itself, like I mentioned earlier, this analysis does not provide all the answers on the correlation between COVID-19 and transit ridership count because of my limited data set. But however, like I mentioned, this analysis can serve as a baseline for further research on this issue. So future analysis regarding this issue could include, like, okay, say for example, if somebody wants to analyze the socio-economic impact of COVID-19 on the transit ridership, or my project can serve as a baseline for that project as well. And thank you all for listening. My name is Arvin Tikefo, and this was my final presentation. Thank you.